Hello again and welcome. This will be part 6 of my review for the Gossen Metrawatt Metrahit Ultra. This is the model M248B. We're going to start this video out with a real basic test. What we're going to do is be connecting this up to our transient generator, and we're going to be applying a 220 volt rectified AC signal, and I'll be applying that waveform with the meter set to all of its different functions except for the current. Of the meters that I'm showing here, this TPI 194.2 is the only meter that had failed this test. Other meters that I looked at that were damaged during that test are the Unity UT20B along with the Tech Power TP2844R. And of course we've ran quite a few meters, so again 3 meters out of all the ones I've looked at, it's pretty rare. So let's just see how this Gossen Metrawatt will do with this test. Alright, we'll just go ahead and turn it on. One of the things with this particular meter, they have a safety feature, I guess, where they don't allow you to actually change the function of the meter if there's a voltage present that's higher than, I think it's like 40 volts. What we'll have to do is turn that signal on and off using our transient generator. So let's go ahead and get started. So you can see the meter is reading 119 volts AC. That's pretty normal. 268 volts in AC plus DC and 230 volts DC. See, it reads high volt. Now what I'm going to do is turn this off. Alright, so then what I'll do is reapply the transient. You notice that now it doesn't display the high fault. You do get the indication here. Let's try changing the switch. High volt. Turn it off. Again, we'll reapply. Notice again that the enunciation for high volt does not show up. So that's it. Let's see if the meter is still functional after all that. Like I say, it'd be pretty odd to have a meter actually fail this test. Normally only the real low end ones do. So let's just start, I guess, with capacitance. This is a 150 picofarads, 1 nanofarads. This will be a 0.1 microfarad, 1 microfarad, 10 microfarads, and 100 microfarads. This should be roughly 500 degrees Celsius. Looks fine. Continuity test. Looks fine. This will be a 0.5 ohm. I'm not going to zero this out. That looks fine. There's a 1 ohm. Looks good. 50. And 100. And 1K. And 10K. 100K, 1 meg, and 10 meg. Those appear fine. So our frequency input, you can see it's 60 hertz. Let's try DC volts. It should be roughly 5. Looks fine. AC plus DC. That looks fine. Let's try AC volts. And we can see it's 60 hertz at 2.5. And this is with our DC bias, so again, this should be roughly 2.5 volts of DC offset, which it is. And this will be at 30 hertz. And you can see that's fine as well. So it looks like it passes this test just fine. Again, pretty much what I would have expected. Okay, for this next test, we're going to be applying a small static discharge directly into the inputs of the meter. And again, we'll be applying 5 transients, both positive and negative, in each mode of the meter. But before I run this test, I've made a promise to one of the viewers, and that's that I would run this test first. So this is our small grill starter. Now, of course, I've shown what the transient looks like coming off of this, and I've also showed the transient coming off of this. This very closely represents the actual IEC standard. This thing doesn't even come close to it, but of course This grill starter has damaged an awful lot of meters. And one of the meters that's gained this thing a lot of fame was this UT181A. Of course, this meter was damaged with a single hit off of this small grill starter. I couldn't believe it. But I have had quite a few Unities that were damaged from this. You know, if I kind of look through the list, of course the Unity UT61D, the Unity UT61E, the X-Tech EX530, the Vichy VC99, and the Unity UT181A. Those were all damaged from this test. In this meter, basically being a very high-end industrialized meter, you'd expect this thing is going to survive this without any problem, but you wanted to see it, and I have no problem running this test because I've said it before, if you have a meter that fails from this little grill starter, that's got to be one crappy ass meter. So there we go. This will be 5 transients, positive and negative, in each mode of the meter. Let's just see who won, the grill starter or the Metrawatt. Let's just start with the AC volts. Like I say, hard to believe that this meter would be damaged, but so again, this will be roughly 2.5. That looks fine. And let's try it at 30 hertz. You can see it's just fine up here. 15 hertz, no problems. And you can see the AC plus DC value. And here's our DC value. This will be roughly 5 volts. That looks fine. Frequency. There's our 60 hertz. That looks fine. This will be a 0.5 ohm. That's fine. 1 ohm. 50 ohms. 100 ohms. 1K. 10K. 100K. 1 meg. And 10 meg. Continuity test. Looks good. This will be our temperature. Again, this should be roughly 500 degrees. Looks fine. You can see I can vary it. No problem. This will be roughly room temperature. This will be a 150 picofarads. Looks good. 0.1 microfarad. Here's the 1 nanofarad. 1 microfarad. 10 microfarads. 100 microfarads. I almost forgot, we should be checking the diode as well. I keep forgetting that you have these other symbols on the back side. So let's just try it with a short. That looks fine. Of course, I didn't test this after our AC line check. That looks fine. That's fine. This will be 3 diodes. And that's fine. The RTD, I don't know if we have something that's kind of close. This will be a 1K ohm. Let's try it with 100K. How about a 10 meg? So it looks like the meter survived this just fine. Okay, so the next thing we're going to do is our ESD test using my larger transient generator. And again, we'll be applying both positive and negative pulses, 5 each, using each mode of the meter. So here we go. Of course, I've tested this on every meter that I have that's functional now, and no meter has failed this test, but that's it. We'll go ahead and functional test it. This will be our 2.5 volts AC at 60 hertz. That is correct. Let's bring the camera in a little closer for you. This will be at 30 hertz. That's correct. AC plus DC. That's correct. Let's check the DC level. That's correct. Here's our 5 volts. That's correct. 60 hertz. That looks fine. And this is an open. That looks good. There's our 0.5 ohm, our 1 ohm, 50, 100, 1K, 10K, 100K, 1 meg, and 10 megs. Here's our continuity test. That looks good. And this will be roughly 500 degrees. Looks fine. And capacitance again, this will be our 150 picofarads, 1 nanofarad, 0.1 microfarad, 1 microfarad, 10 microfarads, 100 microfarads. And again, I forgot to check the diode, but I'm sure it's going to be fine. Again, this will be a short. Looks good. And a single diode, 2 and 3 diodes. That looks fine. So yeah, it looks like the meter survived that just fine. No problems at all. So a lot of you have been waiting for this next part, including myself, for quite some time, basically since I bought the meter. I think it's time to take this thing apart and let's just see what's inside of it. So let me grab some tools and clear her off the bench, get things kind of cleaned up a bit, and then we'll go ahead and take her apart. Alright, let's have a look. I had watched Dave's video taking this apart, and it looked like he had struggled when he went to separate the two halves. And another member made a video for me. I had linked to that. Showed the whole thing coming apart where he didn't speed up the footage. When it got time to split the cases, indeed he ran into the same snag that Dave had. But it looks like there's a couple of latches internal of the meter, and they're just kind of hard to pull it apart at that point. Again, this just uses a standard T10. Ooh, I can hardly wait. I don't know about you. I'm assuming this thing is going to stick the same way that the other two meters were shown coming apart. But we'll see. Maybe this one will just fall apart like butter. You kind of doubt it, but... Okay, yep, sure enough, right there, she's stuck now. Basically, it looked like they had just pulled this thing apart, and eventually the snaps gave. Wow! Holy crap! Alright, boy, you would not believe how tight that is. Holy smokes. Right there. Oh, wow. Oh yeah. Right there. Here and here. So those engage. Yep. See, those engage into those two receivers. Right here and here. Wow. Well, if I had to guess, I would say this is our Bluetooth board. There you have it. Looks like they hot glued the back of the connector. I guess that's how they get their seal, but you know, that's not going to keep water or anything from going down inside of the jack on this side. I'm surprised they don't give you some kind of a rubber plug for this. If they do, they probably charge you $100 for it. You know, that's $70 for that stupid magnetic hanger. I think this company would nickel and dime you no matter what. Meter as a whole looks pretty good. I think the first thing that I want to do, you know you want me to do it too, put this thing back together, slide some batteries into this thing, and let's just see how it behaves without that Bluetooth module. Alright, we'll go ahead and install our shorting strap. Wow. Ha! Look at this. Well, this is a lot better, I can tell you that much, at least from running my hand by it. This definitely has something to do with it. You can see they've just purchased a off-the-shelf Bluetooth transceiver, and of course you would expect that because nobody in their right mind is going to pay to have something like this qualified for FCC. So while the RF effects may have diminished, I mean, I've got my hand right on the side of the case there. That's a lot better. Just detach my strap and let's charge up the cloth. Again, just rubbing this across my hair. Oh yeah. There, I'm not even very close to it. Yep. So you can see, as far as the static is concerned, that still affects the meter. So looking at the inside, here's our culprit. You can see just the one relay. Not too surprised by its location based on where I was running the magnet by it. You know, Dave had shown one meter and they had a shield going across this entire area. Of course, you don't see any shielding in this meter at all. I suspect that's part of the reason why the meter is so sensitive to the static fields. What do you think? Look how crooked that is. Huh? There's our large current shunt. Here's our gas discharge tubes. Looks like just a single MOV and a single PTC. I think what I'd like to do is maybe trace out some of this. Sometimes I wish I'd just leave the camera on or take some better shots. I'll have to go back and have a look. This should show up on the camera right here. This was touched with an iron. And right here. Now I swear I didn't do that, but first of all, I think I'd smell the plastic burning, which I did not. I have done stuff like that, but I think that that may have been there from the factory. Anyway, no point crying over it now. Let's have a look. I should be able to lift the circuit board out of here now. There she goes. Yeah, I wonder if that's kind of a gear system. Kind of looks like it might be. I think this would be your pivot point here. Huh. Well, it's just got the one lowly shield. It's quite the contacts on the switch though. You know, I think the way this would have worked is you have, so here's a via here, and here, and here, and here. And I'm guessing that there could be a shield that would go on the back side that would form into those four holes. I wonder if we had populated that, if that would help our sensitivity to the static field. Huh. But what I'm wondering is if we made a shield that fit between the two, have the holes cut out for the two feed-through connectors, could we improve it? Alright. Well, let me spend a little bit of time and I'm going to trace out the front end of this thing. Alright, so a couple of things I noticed. First of all, if you go back and look where I just took the meter apart, you'll see this slight burn mark right here. That was before I actually took the circuit board out of the meter. So indeed, that was there by manufacturing, it looks like. I don't especially care for this kind of design where you're hand soldering these in. It actually almost looks like it could have been a leaded solder. And obviously, if you look at this board, I mean, this appears to be lead free. As a matter of fact, if we take this out and we look at the shield, I don't know how well this will show up with the camera, but you see this joint? Hopefully that'll show up good enough. I'll try to get it in the light a little better. But that joint is just very shiny. And again, you look at all the rest of the joints on this board, they're all very hazy. And again, you can see the flux residue right around the joint. And I believe that this is being hand soldered, just like the connection points here. Again, you can just see how shiny this is. Again, they may be using leaded solder for this. You know, for RoHS compliance, I don't know if you're allowed to do that. And it's certainly not a good idea to be mixing solders in the first place. But anyway, the next thing I noticed with this, I would have liked to have shown you what the shutter assembly looks like. Unfortunately, this doesn't appear to come apart. So I could probably get the switch out of here easy enough. It looks like there's just a couple of clips. This assembly here would probably pop out. But this assembly right here that actually holds the shutter, I don't think that's something that's just going to come out of there without breaking the meter. So I started to reverse engineer the front end of the meter. This connection here is the volt-ohm input. And there's two resistors. One of these is a 683 ohm, the other one is a 150k ohm. So this 683 ohm is in series with this PTC, and then the PTC goes to this gas discharge tube, which goes to this MOV, which then goes back to the common point. The second resistor goes through this small fuse, and then there's like two resistors in parallel with the fuse, and that goes to this other gas discharge tube, excuse me, this one here, which also goes to the same common point to the MOV back to ground. So these are our primary protection right here. Then the common point of this goes off to this film resistor here, and it goes to a 50k ohm resistor, and that looks like there's a capacitor and a resistor in series, which are these two here that also go to that same node. Coming off of the other side, it goes to this blocking capacitor here, and then that goes up to this larger film resistor here. This is a 10 mega ohm, and you'll also notice that there's this small ferrite bead in the corner, and that runs off to pin 9 of this relay. And you can see that pin 1 by the square pin is right here. There's these 4 pins here on this side make up the 2 coils that drive it. It's a latching type relay. It's actually made by Panasonic. It's a part number DS2E-SL2-DC5. The SL2 designates that it's a latching type relay. The S means it's a high sensitivity part. I believe, again, had they placed the shield in here, depending on how far that shield actually goes back, that may have prevented this relay from tripping. So I'm not so sure that they didn't really shoot themselves in the foot by adding this Bluetooth. First problem is it drains the battery like crazy, and if this shield were in place, the meter may be much less sensitive to the static fields that I'm seeing. But again, if the shield comes down over this area, it could also keep this relay from tripping from an external magnetic force. Just hard to say. You know, I don't have the shield, so I'd have to make something up, and then that would be my shield, not what they actually ship with the meters. But again, I'm not so sure that you couldn't make something for this meter that would fit in between the two boards. So the MOV that they're using, this is a TVR 07821. It's a 7mm disc, of course. With 1 milliamp applied, it'll break down at 820 volts. It's rated for 510 volts AC, 670 volts DC, has a peak breakover of 1355 volts, and it's 71 joules. Yeah, it's a fairly good sized part. The two gas discharge tubes, these are an ES 1200 16O, and so these are 1200 volt parts. And again, these are going to switch quite slow, but you can see they've got some diode protection downstream of this, and hopefully that's enough to save the meter. So if we look at the relay itself, pin 9 is one side of the contact, and 13 would be the common point. Pin 13 runs up to this diode array, and that's located right here. These two diodes here are placed in series and then go back to the common point. The other side runs to this diode, which then goes to the top side of this, what appears to be a Zener diode, which then goes back to the common point, and then there's a 100K resistor that taps off of this. And then on the high side, there's a 996 ohm and a capacitor that also comes off of this, and those are located here. But again, I don't really have any idea if this is actually going to save the meter. We would just have to test it and try it. I'm actually kind of surprised that they didn't push these down a little further. Of course, this is our AC input capacitor here, and again it goes through this 10 meg, but you notice this same node again goes through the ferrite bead, through this relay, which is normally set between pin 13 and 11. But what we're doing is we're applying a magnetic force, we're throwing this into the other state. So pin 9 now goes to 13, which goes right across this clamp. What ends up happening is when this relay throws, it basically grounds out this side, and this PTC now basically is handling all that current. And that's why the AC voltage at this point basically is reading 4 volts or so. And then as this PTC continues to heat up, this voltage just keeps dropping lower and lower and lower. So that explains why the magnet is actually affecting the AC volt only. So it all kind of makes sense what it's doing. I think before I do any kind of destructive testing, the one thing I'd like to do is try to make a shield for the back side of this. So what I've done is I've snipped up this small cardboard shield. You can see how this will kind of fit in here. It'll just be a couple of slots. This will just fold up, and this will hopefully cover up the area around that relay. This is the material we'll be using. This is a 10 thousandths thick mu metal, and to prevent this from shorting, I just have some high density plastic, and we'll lay this between the metal and the circuit board. Alright, so again, the meter's back together, less the battery cover. And I also didn't put the 4 screws into it. Shouldn't matter for this test. So let's just go ahead and turn it on. And you can see I have my jumper installed. You'll notice the input's drifting a little bit, but we now have a offset of about 180 microvolts. Look at this. Just touch the sides of the meter. That's pretty good. Let's try to zero this thing out. Wow, that's a whole lot better. Let's try touching the meter. Alright, you probably can't hear this thing switch with the boot, but we do have this. Just show you that it's on. Anyway, so wow. That's leaps and bounds better. Huh. Well, there you have it. Let's put this thing into Bluetooth mode. Oops. Okay, let's see now if it has any effect. It looks real good. Huh. So that shield makes a huge difference. Let me just try to link to the meter using the PC. Looks pretty good. So my PC is probably close to 7 or so feet away right now, and it's having no trouble connecting to this. What I'm going to do is just rotate it. Yep, no problem. It's still connected. Yep. And still connected. Let's try it down. Still connected. You can see in the upper right, it's definitely pulling the data off of the meter. So, yeah, that looks real good. So let me just show you what I did to this meter. After I'd cut up the shield, I didn't realize like there has to be a notch in this location and one up here. There's a couple of little nubs that stick out, and those lock that circuit board in place. Again, this is our Bluetooth board here. And this is our piece of high density plastic. And what I'll do is just unsolder this real quick. This is kind of what it looks like. Again, this just kind of fits over it. Alright, let's go ahead and reinstall our Bluetooth board. And we'll snap our meter back together. I'll tell you, I'm not impressed with these battery clips. You go to slide the cover on, you have to be very careful that those actually are going through the holes. They bend very easily. The only thing I don't like about this case is with this art design. You see how you can start it from the back and then work your way to the front to push it back together. Unfortunately, when you go to take it apart, you end up pulling off the back first because of these latches here. It's just kind of a bad deal. I think if they'd gotten rid of these latches, this would be a lot better case design, but you know, I don't know. It's not my design. I guess I shouldn't worry about it. Alright, so let's just see what our offset voltage looks like now. So DC millivolts. Huh. Well, that's interesting. It's even higher now without the shield in it. I wonder if there's something else going on as I'm touching the circuit boards or something. So what I'm doing is moving that Bluetooth board. Wow. Yeah. Unfortunately, this appears to be a very sensitive design on how it goes back together. So I think that offset is unfortunately something I'm just going to have to live with. Shouldn't affect the testing that we're about to do to the meter, but again, just something to be aware of. So I think what I'd like to do next is put the meter back together, and then we'll start the transient testing. Didn't have the current input wire attached, and I really just tacked these other two connectors down. And I'm not a big fan of this soldering setup that they've got. I've seen it before in other meters. It's just, I like the ones with the screws with the locking washer much better. But you know, soldering's a lot cheaper. So when you're getting cheap meters like this, I would expect to see stuff like this. Alright, let's see if you can see this right here. It's some kind of contamination that's stuck behind the LCD and the glass. Now I haven't had this section apart at all. It's just been laying out on the table. But I'm not so sure that when I was doing my little cloth rubbing with the static charge that we didn't just suck this thing up from somewhere. Well, I'm not going to take it all the way apart to get that speck out of there. So anyway, so I've installed the back cover and the fuse is installed. So let's just see, with everything being soldered now, what's our offset voltage like? Alright. About the same. It's hard to believe that the room temperature would affect it that much. Uh-oh. Now we're back to normal here. Just got the cloth out. Oh yeah, you can see already. Should have probably... I mean, I'm just coming up to it right now. It's probably more than a foot away still. Oh yeah. 2 millivolts again. And of course we're back to this problem again. Let's just see. Oh yeah. So it would trigger it up from the front as well. Yeah. And of course off the back, pretty easy to trigger it. So it looks like that shield does a pretty good job. Yeah, that dust speck is going to bother me. There, it just flipped. Damn it. Well, I think that's going to be it for this video. I think we've got more than a half an hour. I think for our next part, we're going to start transient testing it. And we'll just see where we go from there. So long for now. Until the next video. Later.